Okay, so hello everyone. Welcome to the revision session of C programming. So today we have with us Subhashish Das. So Subhashish is one of our same students, and he is also the TA. So you can ask doubt if you have any. So feel free to unmute and ask your doubts. And Subhashish, over to you.
Thank you, thank you, Abhishek. So, hello everyone. I'm Subhashish Das. I'm currently in my last term of diploma, and I'm an ES student just like all of you. And I'm currently the teaching assistant for this term in C programming. And yeah, if you guys have any doubts and such, you can feel free to raise your hand, and I can, you know, you can unmute yourself after that, and we can try clarifying it. And don't worry about the language, like I can speak both English and Hindi, so if you have any doubts regarding that, we can take care of it. Okay, so I see that Gohar has already posted a doubt in the chat. Explain a bitwise operator. Okay, I mean it's a bit advanced for the quiz one. Okay, so before we just start the session, I'll just give some information. The syllabus for quiz 1 is week 1 to 4. Okay, so you'll only be dealing with like the theory stuff from weeks 1 and 2 and the conditional statements, and after that the loops. So other than that, there's nothing that will really come. Okay, not even functions are coming. So it's you don't have to worry too much about the syllabus. And I'll be mainly focusing on the practical aspects, so like the programming technicalities and stuff, since I'm not really all that good with theory and history. So yeah, you know I hope that you guys know what to expect in this class. We'll be discussing mostly about the technical aspects and the corner cases in order to get a better understanding of the programming in general, and we'll be limiting it to loops. So function and all that will be doing for quiz 2. Okay, so I'll just be presenting my screen, and I'll ask a f- I'll ask a couple of questions to get us started. So first question, where I've seen quite a few people having doubts, is with 2's complement and positive and negative numbers. So sorry, number representation in computing. So let's say that we have normally what we write, we are using a decimal system. So have 10 digits to choose from, or 10 numbers to choose from, I guess I should say. Okay, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, 10 is not really 10 is not a number, it is a combination of numbers. Sorry, 10 is not a digit, it's a combination of digits. So we are using 1 and 0 to denote 10, so that is not a single digit. These are the 10 symbols that we use for a decimal system. Similarly, for a binary system, we just use two numbers or digits, which is 0 and 1. Similarly, for octal, hexadecimal, and stuff like that, we just have a different number of digits that we use. So these are what we call base n number systems. So decimal number is base 10 number system. Okay, and a binary is a base 2 number system. So this is like that. Octal is base 8, hexadecimal is base 16. You can have some odd base numbers as well, base systems as well, such as base 7 number system. Okay, so these are all just different forms of expressing the same number. So let's say that I have some number, let's say 29. Okay, we write 29 like this. What it actually represents is 2 into 10 to the power 1 plus 9 into 10 to the power 0. This is essentially what we refer to as place value. So this is a ones place, this is a tens place. So similarly, if we were to use, let's say 1010, this would mean 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 into 0 into 2 to the power 0. Right? So this refers to this. This refers to this. So can anyone tell me if I say 92 and I'm writing it in a not a normal base system. Let's say I'm writing this in a base 7. And the representation that we normally use to denote base is just a subscript like this. So let's say that I'm writing this in a base 7. Can anyone tell me what this number would be represented as in base 7? Can you guys, one second? Yeah, you guys are free to unmute and say if you have any guess regarding this. Let's keep the session interactive and lively. Yeah, that's correct. So we have 9 times 7 to the power 1 plus 2 times 7 to the power 0. So this is what it represents. Now notice that all of these are simply multiplication and addition. Right? So essentially we can these all refer to a particular number. So if I were to say everything in base 10, which is the normal decimal system, this one is 29. This one would be what? 9 times 7 is 63 plus 2. So this is 65 in base 10. Similarly, what would this be? This is 8 plus 2, which is 10 in base 10. So is this part clear? Like how we use different base numbers or base number systems. So essentially, we represent different numbers using different bases in this way. So I'll just give you one question. Let's say I have 279 in base 10, and I want to convert this into uh, an octal system, a base 8 number. So what can I do?
Should
Okay,
divide
so
it by 8, I think so.
right. So what should we divide this by?
8.
Right. So we can try dividing this by 8. So if we divide this by 8, then what do we get?
The quotient will be one side and the remainder will be leftover remainder is going to be
Right.
whatever will be there will be come back.
So let's just say it is what? We get 30. This is 39. So we get 34 along with 7 as the remainder. Is this correct?
Yes, sir.
Okay, so after that we can just go once again. So it will become 2 with 4 as the 4 with 2 as the remainder, and after that this is remainder in itself. So what we can conclude from this is that it is 7 times 8, okay, plus 2 times sorry. So essentially what this means is that this is 2 times 8 to the power 2 plus 7 times 8 to the power my mistake, 4 times. Okay, just give me 1 second.
4 times 8 to the power 0. I think so, something like that will be there.
Yeah, I don't really use this method, so I'm not familiar with this. I just simply take the closest power. So in this case, I believe it would be 8 to the power 3. So
Yeah.
64 times 8, what would this be? This is 20, 32. This is 48, so 512. Okay, no. So it's 64 only. 8 to the power 3 is way too big. So we can divide this by 64. So 256 we are getting. So 4 into 64 plus 256 minus this is 23. Is it? Uh, 23. So that is, yeah, 2 times 8 plus 7. Yeah, so the method that we got was correct. Except this is 8 to the power 0, this is 8 to the power 1, and this is 8 to the power 2.
So
So
basically, you have to whatever is there, just how many digits are there, just reduce that by 1, and then keep on as a progression. Like if it is 3, then 2, 1, and 0. If it's 4, then 3, 2,
right,
1, 0. Right?
essentially that, yeah. So the final number that we get, x is equal to 427. Okay, so 279 in base 10, we can write it as 427 in base 8. So that is essentially how we convert this one. So a few tricks that I'll give you guys. Let's say that we have A697. And normally for hexadecimal, we write it like this. So I want to convert this into binary. How can I do this?
So what is this 0x in the starting?
That is typically how we denote, and that is how we denote it as hexadecimal.
Okay, but any meaning it has? Like just for denotion, you write it like.
Just for identification. It does not really contain any significant meaning that you have to worry about right now.
Okay, then why can't we remove that?
Because otherwise, it is not really clear whether we are using base 16 or some other, like let's say base 20, we could also use.
Okay, like for example, for other bases also we would have letters in it. So not to confuse it, like we write 0x in starting.
Yeah, something like that. So I want to convert this into binary. So how can I do this quickly? Okay, so this is a trick. First, I want you guys to calculate what this would be in binary, like properly, like methodically. And Priyal, I see that you had given the correct answer, so good job for that. Okay, so can anyone tell me what would C, this one be in binary?
So A is 10. So in that way, it will be, I think so, it should be 13 or something like that.
Uh, let's say like it is going to be 12, right?
Okay. It's going to be 12. Okay.
Sorry, no, not 12. Yeah, it's 12, I believe. 11 is B and C is 12. Yeah.
11 is story.
Yeah.
Yeah, it will
So,
be 12.
12, it will be. Like we start from 10. No? A is 10, B is 11.
yeah. So C is 12. So 8 plus 4, 0, 0. So this is essentially how we represent it. It represents C in binary. And I see Diksha is given the correct answer. So good job for that. So this is how we represent C. Now, what about 2C?
Zero zero 1 0 1 1 0 0.
00101100. That is correct.
Yeah.
So what I want you guys to notice is how this part is the same as this part. Okay. So one interesting thing about hexadecimal is that every digit, it corresponds to exactly 4 bits or 4 places in the binary notation. So even if we have like a 20 or 30 digit long number in hexadecimal, it will correspond to a 80 digit long number in binary, and you can individually calculate each of the 4 bits without it affecting any other. So that is just an interesting property, and it will help you to quickly and effectively convert hexadecimal to binary. So for example, this one I can say it's 4 bits, 4 digit hexadecimal number. So it will be 16 bits long, right? So I'll just start from A. So A is what?
1010.
A is 10, right? So yeah, it's
Yeah.
1010. What about 6?
0110.
0110. What about 9?
1001.
Yeah. What about 7?
0111.
Yeah. So that is the power of this trick. Just you can directly convert without much effort. Just you have to know how to convert from, you know, a single digit to decimal. Sorry, a binary. Are there any questions in this one? Because mostly you'll be converting from hexadecimal to binary, or maybe from hexadecimal to octal. Okay, so if anyone has any questions for this one, for hexamal to decimal or bit the number system conversion in general, feel free to ask it now before we move on to the next part. Okay, so here's one question. I have an 18-bit long binary number. Okay, I'll just fill it with some numbers. So I want to convert this into hexadecimal. What will the number be? First, before converting this, tell me how many digits long the number will be in hexadecimal.
It's like the binary number which you have written, it's 14-bit, right?
No, it's I believe, one second. Yeah, it's 14-bit. Yeah. I'll just add 4 more bits. I meant to use this as an 18-bit number. So yeah, my bad. But yeah, how many digits long will the hexadecimal number be of this one?
It will be 16, right? 16-bit.
How many digits, I'm asking, will the hexadecimal number be? Like over here, we converted a 4-digit hexadecimal into 16-digit binary number. So I'm asking, how many digits will the hexadecimal number be of this one?
5.
That is correct. In order to represent all the data, we need 5 decimal places. Because if we were to use just 4 decimal places, we could only show up to 16. So these both would be cut off. I mean, in this case, it wouldn't really matter. But let's say that this was a 1 or this was a 1, then that would be like you'd be losing information. So it's always better to go higher if you are even exceeding by 1 bit. So can you convert this into hexadecimal fast? I want answers within 5 seconds. What is 0111?
7.
That is correct. What is this?
1.
1. What is this?
F.
F. And what is this?
E.
E. And what would this be?
So we have to extend. So can we take like 1100, or it should be 000?
See, since it is just 2 digits, we cannot really directly convert it into hexadecimal using the trick. But you know how in any decimal number, if we have, let's say, 102, we can add as many zeros we want to the front. It won't change the meaning. Like it is still going to be 102. So in a similar way, if you have a binary number, you can add as many zeros to the front as you want. It won't change the meaning. So we can just simply pretend that there are 2 zeros over here. And using that, what will the number be finally?
0.
That is correct. So finally, this whole binary number, it translates to 0x0EF17. Okay, does anyone have any doubts in this one? If you have, feel free to say it. Like, feel free to unmute yourself and say it. Okay, it looks like you guys don't have a doubt in the number conversion. So let's move on to negative numbers. So
Shubhashish, just sorry for the interruption. I just want to ask, like, have you done with that resistors and like there's one question, right, where we have to like convert memory goes to register, then register goes to memory. That one, like M0, M1, R1, R2.
okay, so you want me to tackle that one first?
Yeah. So like, if you can tackle that, because I have seen like 2 to 3 questions there in mock, and I felt difficulty to solve it.
Okay, so essentially that is similar to like assembly level languages or what we are instructing the machine to do, right? So let's say that we have some R some X memory location. X is an integer, okay? So X is simply an integer. So this refers to some memory location in a register. I hope you guys remember the computer architecture. So in the center, we have a CPU. Close to this, we have the cache memory. And a bit further away, we have the registers. Or I guess it would be RAM, then the secondary storage devices, SSDs, and stuff like that. And the CPU itself is connected to the ALU. So this is like a very basic like computer architecture, CPU architecture. So what generally happens is that whatever we have in SSD or in RAM, that is loaded onto the cache in this way for a quick access. So if you guys remember, can anyone tell me what the fastest memory out of these three is?
Cache memory.
That is correct. So the cache memory, it usually sits within the CPU. Okay, so it is the fastest. It essentially has like negligible delay. So that's why we generally use loading and storing methods to properly utilize this. So let's say that we have some program stored here. Like there are different memory locations everywhere. So let's say that this is 0, 1, 2, 3, 4. So we are taking from memory address location 4. And we are storing it onto, let's say, like address location.
Hello,
Three.
sir. Good evening.
Yeah, Prashant.
Sir, I joined right now. So, how much is covered?
We just covered the number conversion. You're still quite early. Don't worry about it. Okay, and even so, like this session is being recorded. So I believe that you guys will be able to, revisit this session if necessary.
Okay.
Okay, so we have some program in location 4. So the SSD is quite slow in comparison to the RAM and the cache. So we generally take this into the RAM and store it somewhere before using it. So let's say that we are taking from memory location 4 and storing it in memory location 3. After that, let's say that we only have 3 locations in the cache memory. And we are storing it from the RAM into memory location 1. After that, the CPU works with it. It communicates with the ALU and stuff like that. And let's say that we have finished work with it. So we are putting it back into the RAM. And let's say that we want to permanently store it. After that, we put it into this secondary storage or SSD, hard disk, whatever you have. So this is like a very bare bones explanation or a very light overview of how a CPU works or how it uses data and memory. So what we mean when we say M of X or R of X, it typically refers to a register location. So it may refer to this or this, but M of X, so M of X almost always refers to some form of permanent storage, be it hard disk or SSD or stuff like that. And R of X, it refers to temporary storage or volatile storage. So some register or stuff like that. Generally, registers are mostly found in the cache memory. And the random access memory, it also contains like some level of like some slower registers. So generally what we say, like this is just a convention. It is, there's nothing defining that whatever is stored like this, it is loading or this is storing. But for our purpose, if we take some memory from a location in register, let's say the zeroth place in R. So we are taking data from here and we are copying whatever data is in there into memory location, let's say 2. So if we are copying this from memory location 0 to, register 0 to memory location 2, then that is called storing. Okay. So we are going from a uh, non-permanent memory into permanent memory. So we store the data from a non-permanent source to a permanent location. And if it is going the other way around, if we are copying some memory from, let's say, memory location 1 into register, I don't know, 2. So let's say that we are going from memory location 1 to 2. So this will be called as loading. Okay, you may have seen the loading screens on games, or you may have seen the buffering on YouTube videos. So this is essentially what happens. The data that is in some form of permanent storage, that is being copied onto your RAM or registers, so that it can be played back a lot faster, a lot smoother. Because if it was played back from the SSD or something, it would be quite slow and quite choppy, in all honesty. But yeah, storing, essentially we are copying from register into memory. Loading means we are copying from memory into register. Is that okay? Anyone any doubts? Okay. So now can anyone tell me what does this code refer to? Sorry.
Like first one means like we are loading some data from memory 1 to register 1.
That is correct. So let's just assume that M0 contains the value 0. Okay. One second. Let's say that M0 contains 0. M1 contains 1. Okay. So now can anyone tell me what is in M5? Like, I'm asking the numerical value in this one.
Answer two.
Sorry.
Two, sir.
That is correct. So it will contain 2. What about M6?
Again 2. Sorry, sir. One, sir.
That is correct. So it's 1. Now, what about M7?
It's, 2.
That is correct. It will also be 2. Now, tell me the values in the registers. R1, R2, and R3. Actually, no, this is a very simple question. So, let me ask this. So, what is in R2 right now?
One.
That is correct. So these are all like this is simple instructions. It's not really something too complicated, but you have to recognize that we generally have some stored data. Okay, let's say 0, 1 or something like that. And we copy that into registers in order to utilize them. Notice how I'm not using the only place where I'm using the memory locations is for loading and storing. They are not where operations are performed. Okay?
So Ashish,
Yeah, Tarun.
like here, like M0 goes to M1 means it means load. So it means now R1 is 0, right?
Yes.
And then M1 stores to R2. Then it means R2 value is 1, right?
See. Just use the correct terminology. This is loading.
Yeah,
Okay. This part is storing.
right.
Okay. So the data in M0 is copied into R1. So we are loading the data from M0 to R1, which just happens to be 0.
Right.
Okay. And similarly, we are loading the data from M1 into R2, which just happens to be 1.
Yeah,
Okay. And after that, we are using the registers, the data in the registers to, perform operations.
right.
So here we simply have 2 addition operations, and down here we have some subtraction operation. So that is really all there is to it. And after that, we are just copying the data from here to here. This isn't really like loading or storing anything. It's just assigning this data to R3.
Okay. And in the fourth one, where R1 plus R3
Yeah.
gives goes to then R1, right?
Yeah.
So now it's like the value will be like 3, right? The value of R1.
0 plus 2 equal to
Keep in mind the value in R1 is 0.
Okay, sorry.
So this is 0 plus 2.
0 plus 2. Okay, so it will be 2. Now
Yes.
the value of R1 will be 2.
Yes.
Okay.
And after that, we are just storing them into some memory locations. And yeah, so in the end, it's 2 minus R2, which is 1. So we get 1, which is the same value as before.
Okay, got it.
Okay. Anyone else, any doubts?
And then in the last one, where like R1 minus R2. So
Yeah.
like now like R1 is 2, right?
Yes, R1 is 2.
And R2 is 1.
Yes.
So like we are doing like basic subtraction, 2 minus 1, then it goes to R2, which is then R2 becomes 1.
Right.
Okay. Great.
Okay, so don't take this problem too literally. This is just to help your understanding of the concept. So whatever operation you perform, we are storing the value somewhere, or we are updating some register with the value from this operation. So this is how assembly language generally functions. It's a bit more complex than this, but yeah, this is the basic gist of it. Okay, so if anyone has any doubts, please feel free to unmute yourself. Okay then, so let's just move to the next part. Negative numbers. So we have two forms of negative numbers. We have the signed form and we have the 2's complement. Okay. Generally, the signed form is outdated. So we'll just use the 2's complement. Just assume that any negative signed number, if it tells you, then that is 2's complement. So we have two different numbers now. We have unsigned and we have 2's complement or signed. Please pardon my bad handwriting. But yeah, so we have unsigned and we have 2's complement. So unsigned, it simply means treat the binary number as it is. Do not take any convention, do not take anything. So if we have 1001, then this is 9. This is not some other number. Now, if it was in 2's complement, how would we approach this? Essentially, what 2's complement means is that if we want the negative of some number x, let's say that we want a negative of 9. I'll just make this 5 bits so that we can actually get negative 9. So if we want negative 9, in that case, we would first have to write down the binary representation of positive 9. Then we would flip it and then add 1. So this is what negative 9 looks like in 2's complement. Okay, so here's a question for you guys. Why do we need, sorry, not why do we need, but how do we get 2's complement? Like, why is this the negative number? So here's one question. If we were to first answer the previous question, why is this considered as negative number? Why is this representation considered negative? You can take any guess, like even if it's wrong, we'll learn something. So feel free to take any guess. Okay, not an issue. So can you guys tell me what happens when we add 0, 1, 0, 0, 1 and 1, 0, 1, 1, 1? What happens when we add this? So keep in mind, this is 9 and this is negative 9. Right, so we would expect this to result in 0, right? That is what our decimal thinking minds tells us. So what do we get when we add both of these? Gohar, that is correct, but that is not the full answer. So we get 5 zeros over here, but we also get one overflow, right? But tell me one thing. If we have a system that can only read up to 5 digits, will this last overflow digit be read? Like, think about this. We have, let's say, 4 bits, right? And I want to make a decimal counter. Like, I believe a few of you have already like experienced the electronics labs. So in that we had to convert from 16-bit to like decimal, right? So from 0 to 15 we had to convert to 0/1 and 029/025. So this is what we had to do. For that we just use 0110 plus whatever number we had. So the reason that stuff like this works is because we are using the overflow to our advantage. Okay, so let me ask you this. If I were to subtract, essentially subtraction is like, this is how we get the negative numbers, right? So 0 minus 2 is minus 2, right? Even if this is like positive 2, we'll get negative 2 over here. So that is typically how we, take this. Now, let me ask you this. What will happen if I did 10 minus 2?
It should be 8, right?
It is 8. So tell me one thing, what will happen if I say 2 plus 8? What is this?
10.
It is 10. Now tell me one thing, if I can only read the ones place, then what will the result be over here? Let's say that I cannot read the tens place at all.
0.
It will be 0. Right? This 1 will be obscured. It will be hidden away. It will be lost. So, is it okay for me to tell that 2, like 8, is negative 2 as long as we are operating in a single digit? Think about it. 2 minus 2 is going to result in 0. And as we discussed over here, 2 plus 8 results in 10. But if we are unable to, see the tens place, then 2 plus 8 also results in 0. Right? So in a system where we are unable to get any, actual negative numbers, this is the next best thing. So we treat 8 as negative 2. And that way we can get negative numbers using positive integers. So for this to work, we have to already define a limit. Okay. So if we, let's say, use 100 as the like limit size. So any number above 100, it will, like, that's the limit. That's the biggest that it will go. So if we have, like, let's say 27, then what would 63 be? Sorry, 73. If we add the both of these, sorry, 100 is not really true in this case. Let's say 99 is the biggest that something can go. We are only using 2 digits. So in this case, adding these both would result in 100, right? But since we are only operating using 2 digits, we cannot see the third digit. 27 is essentially the complement of 73. So these both cancel out, giving us 0, 0. And if we are using a system where we can only get like 2-digit output, this is as good as telling the 73 can be treated as negative 27. Okay, in a similar fashion, like think about it, in binary, we don't have any true negative numbers, right? There's no way of telling whether some number is negative or positive. We only have ones and zeros that we can flip. So we have to take a convention and say that if the first bit is flipped like this, if the MSB is flipped like this, no matter what the following digits are, this will be considered as negative. And if it is like 0, then the same thing would be positive. Okay. So these both are the same number, just that this is negative, this is positive. So now tell me, do you guys understand why the complement, like we use complement numbers as negative numbers? Okay, seems like it was a bit too much information too fast. Can you guys just tell me where you guys are facing any like doubts?
Something we couldn't understand. Why 2's complement only?
Okay, so I'm telling you, let's say we have 3 digits over here. Okay, so I have 0, 1. Sorry, I'm writing this as 0, 1, 1. This is 3, right?
Yes.
So I want to make, and 0, 0 is 0. This is 0.
Yes.
So if I want to make a negative number, so if I have A and I have a number minus plus B, and those both add up to 0, then what can I say? B is equal to minus A, right?
Of course.
Yeah. So by this logic, if I'm able to find some number that when added to 3 in binary form gives me 0, 0, 0, then can I call that number that I found as negative 3?
Yes. Yes.
Right? So essentially what we want is to find a number that when added to this one gives us 0, 0, 0. Okay, so already we are seeing a problem in this one, right? Since binary numbers, they can only grow in value. We have to find some way in which we can get 0, 0, 0 in the first 3 places. After that, what happens? We cannot read. Before that, what happens? We also do not know. We just want these 3 places to be 0. So what can I do? Let's go step by step. What can I add to this one to make it 0?
Again 1.
It is 1.
Right.
So now these both will add up to 0 and we'll have 1 carryover.
Yes, yes.
right? So what can I add to this part to make this one 0?
Again, one more carry
Are you sure about that?
to the left side.
Because see, already we have one carry out over here, right? So this will be added to this one,
Yes.
right? So what are we getting over here? We are getting 1 0 from this one, like this addition,
Again 0.
right? So we are getting 0 already. So we do not need to add anything over here. And we are getting one carry out over here. Correct?
Yes.
So now what can we add to this one? Remember this, there's a carry over here to get 0 in the sum.
1.
1, right? So
Right.
if we add 101 to 011, then we are getting 000 in the first 3 digits. We are getting a carry out over here, but that is overflow. We cannot read that one.
Hmm.
Okay. So these 3 places is what matters. And for that one, this number added to 3, it results in 0. Right? So over here, as we mentioned, if I do 3 minus b equals 0, b is equal to, 3 plus b. So b is minus 3.
Ah,
So can I say 101, regardless of what it means in binary, it is minus 3.
obviously.
So that's the reason why we use 2's complement. Because directly adding 2's complement to a positive number, it behaves as if it is a negative number. Okay. So
Yeah, sir.
similarly, if we were to just do, let's say 01001, what can we add to this to get 00000? Tell me one by one.
1.
1, we get a carry out over here.
1.
Yes, sir. 1.
Again 1.
Again 1.
Again
Again
1.
0.
that is correct. We get a 0 over here.
1.
1. So we get a carry out. We cannot do anything with that carry out. So this is the result. So can I say 10111 is negative 9?
Ah, yes, yes.
Yeah. So this is how we get 2's complement. Okay. Now, as I mentioned before, in order to get 2's complement quickly, we use shortcuts because we cannot sit down and calculate this the whole time, right? We want to save some time. So any number, let's say I have some massive number like this one. Let's do this one. So we have some massive number like this. So directly we can convert this into 2's complement by first flipping this. So step 1, flip it. Flip the bits. So we get 10100110110001111. Okay, so this is everything flipped. Okay, so I'll just pause at this step and ask you guys, what will happen if we add these both now? What will happen if we add the both of these numbers right now? That's correct, Gohar. Every single digit will become 1. Okay,
Yes.
think about it. 0 plus 1, 1. 0 plus 1, 1. 1 plus 0 is
Yes, yes.
1.
Correct.
Every single digit will become 1. So now, if I want to turn everything into 0, what do I have to do?
Adding one more one.
I can simply add 1, right? So
Yes.
step 2 is add 1. So now what do we get? 0, 1, 0, 0, 0, 1, 1, 0, 1, 0,
0
0,
0 0 1 1 1.
1, 0, 0,
Yes, sir.
right? So this is the negative of this one. Okay. That is not the right symbol. This is the right symbol. Yeah. So this is essentially how we can quickly calculate the 2's complement. Okay, so now tell me, what's the maximum size that we can get in a 2's complement? Like, what's the biggest number that we can get?
Two raised to 32.
Are you sure? Like, okay, let's say we have 32 bits.
Yes, sir.
Okay, so what's the biggest number that we can get from this one? Keep in mind, we are using 2's complement. So if we are using the first bit, the MSB, most significant bit, as an indicator to tell us whether or not the number is supposed to be a negative number. So essentially, we have one bit as a sign indicator, and we have 31 bits of data. So with this information, tell me what's the biggest number that you can get, the biggest positive number.
Two raised to 31 minus 1.
That is correct. So
Yeah.
yeah, Gohar also mentioned the correct answer. So good job, both of you. The biggest number that we can get is 2 to the power 31 minus 1. Now, how did we come to this number? Let's think of it like this. Let's take a smaller example to understand it. So let's say that we have a 5-digit number. Okay. Now, this first one is a sign indicator. So it will either tell the number is positive or negative. So we can ignore this for magnitude calculations. So we have 4 bits with which we can work with. So what's the biggest number that we can get from 4 bits? Keep in mind that we have already ignored the sign bit.
Two raised to
Don't use a formula for this one, Gohar. Just tell me by mouth. Like, what's the biggest binary number? It is when everything is 1, right? So this is the biggest binary number possible in 4 bits. And this translates to what? 15. Is that correct? So the biggest number that we can get in 4 bits is 15, which can also be written as 16 minus 1. Right? And 16 is 2 to the power 4 minus 1. So that is how we get this number. Similarly, if we had just 3 digits, 3 binary bits, that becomes 7, which is equal to 8 minus 1, which is also equal to 2 to the power 3 minus 1. So do you notice a pattern here? So the pattern is the number of bits that we are using. The maximum number that we can get is 2 to the power that number minus 1. So for n bits, we can get 2 to power n minus 1 as the biggest number. Is that clear?
Yes.
So now, if we apply this formula over here to the 31 bits, what will we get? We get this one, 2 to the power 31 minus 1. So this is the biggest number. Now tell me what's the biggest negative number that we can get. Okay, so what will happen if we just set everything to 1? Or I guess okay, so we have let's say 4 bits. This bit, yeah, let's say we have 5 bits. So let's say that I wanted 16. That would be this one, right? So what is this? Like what's the 2's complement of this one? This number actually has a special property. That's why I'm asking you to find the 2's complement. So let's just follow the steps that I mentioned previously. Firstly, let's flip everything. And then let's add 1 to it. So you may notice that we are getting the same number back. Right? So since we are getting the same number back, can I say that this number, since this part is always going to be negative, like the 1 indicates that this is going to be negative, can I say that this number is is always going to be negative? It cannot be positive at all. Yeah. So what is this number now? What's the magnitude of this number? It is 2 to the power 4 or 16. Right? This is the magnitude. But because we are using a 2's complement system and we are using signed integers, this 1 in the first place, sorry, in the MSB's place, it indicates that this is going to be a negative number. So if we just do that, the answer we get is 2 to the power negative 2 to the power 4 or minus 16. So can you tell me, is this bigger or is the complement of this one bigger? Can you find the 2's complement of this one? So the 2's complement for this one, it becomes this. Okay. So can you tell me, is this one bigger or this one? Keep in mind that this is, in this case, we are only considering these 4 as the magnitude, since this is its own 2's complement. That's correct. This one is represented as minus 15, and that one is minus 16. A bit complicated, but essentially what you need to realize is in the case of 2's complement, the minimum value is going to be 2 to the power n minus 1, and then the maximum value is going to be 2 to the power n minus 1 minus 1. Is that clear? So if we are talking about a 32-bit integer, the number that we get is 2 to the power 31, sorry, it's supposed to be minus. So minus 2 to the power 31 to 2 to the power 31 minus 1. Is that clear? Okay. So this is essentially like what we have found the maximum and minimum value of a 32-bit integer to be. And keep in mind, this is a signed integer. Okay, so we are using the MSB in order to indicate the sign, whether it is positive or negative. Now, I'll just show you a few alternative representations of this one, since there have been a few questions on this one. So you can also represent this like this. You have a, I hope that you have all read set theory and you understand what this parentheses means over here. Essentially, the square bracket means that we are including the term, including the extreme terms, and the parenthesis means that we are not including the extreme terms. We are including the number below that. So in this case, we are not including 2 to the power 31. We are including one number below that, which is 2 to the power 31 minus 1. So you can pick whichever representation you prefer. And what is being asked according to the question, you just have to see that one. Is this one okay? Others? All right then. So these were some of the topics that were, like mostly questioned about. At least the parts that did not involve any programming yet. So, like next, what concept do you guys want to cover? Or I have a few questions already prepared for programming. So do you guys want to check that one out? Okay, Gohar. So essentially, a bitwise operator is, as the name suggests, operators that work bitwise. So let's say that I have 7 over here, and let's say that I have and 3. Okay, so can anyone tell me what will this return? So generally for bitwise operators, we just use a single special symbol. So bitwise AND is just a single ampersand. Bitwise OR is a single just bar. Bitwise XOR is this one. Bitwise operator is So this is how we represent bitwise operators. And what they do is that they take the binary representation of the numbers and they work with that. Kamili, that's correct. This will return 3 because I do not really need to care about the other digits of 7. But this is 111, right? Let's just add a 0 to make it look nice. And we are bitwise ANDing 0011. Right? So what happens over here is that we AND each bit individually. Okay? So each bit we AND individually. And according to that, we get our results. So 111, again 111, 10, it is going to be 0, and 00 is 0. So that way we get 3 as the answer. Now for another one, let's say that I'm using 7. Let's say I'm using 13 and I'm XORing it with 6. So what will we get? So the way to do this is to first represent this in binary form. So it will be like this. It is 8 plus 4. So this is 13. And we are XORing it with this one, which is 0110. So what will we get from this one? You guys know the XOR operator, right? I don't think that this is being live streamed, sorry. This is being recorded, but it's not being live streamed. Okay, so essentially if we XOR this one, we get 1 0, we get 1, 0 1, again 1, 1 1, it is going to be 0, and 1 0, it is going to be 1. So essentially what we get from that is yeah, the recording will be shared later. So essentially what we get from this one is 1011, which is 11. So if you were to do this with 11, with 13 with 6, then we'll get 11. You don't really need to focus on this one right now. It's not really all that useful for you in general programming. It will come in handy in embedded programming. So don't worry about it. You'll learn about it in embedded C. Is that okay? Yeah. Okay, so let's just move on. I have a few questions set up over here. So let's just solve this one. Okay. 1 second. Is this visible? Okay. So the question is, write a C program to determine if a number is perfect. And what do we mean by perfect? The sum of its proper divisors equals the numbers. Okay, and we have a example over here. So essentially what this is telling is, let's say for 28, as you can see, it is already auto-completed. We have the proper divisors of 28. So 1, 2, 4, 7, and 14. And these add up to 28 itself. Right? So this is the perfect number that we want to find. And I've already got some boilerplate code over here. So can anyone tell me what the first step should be for this one?
Here we need to divide the number.
We need to find the factors, right?
Yes. Yes, factors.
Yeah. So I'll just create a few variables over here. So we need sum over here, right?
Yes.
So we have to find all the factors, right? So firstly, we'll need a for loop over here. Okay, this guy is way too fast. But yeah, uh, what should the initial conditions for this be?
2.
Should I start with 0 or with 1?
1 is okay. Not 0.
Are you sure? Since we
Yes,
are
we
trying to find factors and we want to divide the number by I repeatedly in order to find the factors, we should start with 1. Since division by 0, it leads to undefined,
yes.
right? So yeah, after that we have to go up until. Okay, so tell me, do we have to go up until n, or can we stop before that also? Like
Stop.
this should give you an example, like a hint.
Yes, yes. It's less than n.
Yeah. So no, in the sense we can stop. Uh, we can stop by n by 2 already,
Yes, yes.
right? Because if it was going to be any bigger than n by 2, it has to be multiplied with a smaller that is less than 2, if that makes sense. So let's say that we have some number n and we are going up until n by 2, right? So in order to get n from n by 2, we have to multiply this by 2, right? So 2 into n by 2, it will give us n. Now tell me what will happen if we have a number that's um, bigger than n by 2. Or let me just put it like this. Let's say I have a k where k is bigger than, this is bigger than n by 2. So what can you comment about k? At this point, we can just cancel this one. So it is 1 by k is bigger than 1 by 2. So what does k have to be in order to get n back? K will have to be less than 2, right? So what we can see from here is that n by 2, if any number is bigger than n by 2, in that case we'll have to it will have to be multiplied by a number that is smaller than uh, 2. So n by k in k into k, sorry about that, n by k into k is equal to n. So if k is smaller than 2, sorry, n by k is bigger than n by 2, then that will imply k is smaller than 2. And what this means is that k, an integer, will have to be smaller than 2, which means only one thing, that it can be 1, right? And we have already counted for 1. So it does not matter. So we do not have to go beyond n by 2. That's what I'm trying to say. Anyways, I believe that you will be able to reason that out later. So I've gotten this far. What should I do next? So can anyone tell me what I have to do in this code next? Before that, just a quick audio visual check. Am I clearly audible? Is my screen visible?
Yes, it's good.
Yes.
Okay. So can you guys just tell me what I have to do over here?
We just need to simply divide by I.
Okay, so n divided by I, you're telling.
Yes, that equals to.
So we need a if condition over here, right?
Yes,
So do we want n divided by I or n modulo I in order
and
to
modulo
check the
I.
for remainders? N modulo
Modulo.
I.
Modulo.
Yeah, that's correct. So we are essentially checking if a given number. Okay, we are essentially checking if a given number is a factor of n, right? If it divides it completely. So what should we do if it divides it completely?
Simply save that number.
Right, we simply add that number to sum.
Uh,
That is correct. So after this for loop, what do we have to do?
we just simply check again whether the sum value is equal to the total, the correct previous
If
number.
sum equals n, are you telling? If sum equals n, after that it's just printing like that. So yeah, that's essentially the code that we have written over here. So did you guys get what we did?
Yes.
Okay. So now to just test this one. Okay, so it's telling me to enter a number. So I know already that 28 is a perfect perfect number, but it is telling that it is not perfect. So why is that? Where did we mess up? Can anyone tell me? It is a very small, it's one character that is causing the mess up. So try to find it.
I think sum is equal to plus is equal to I लिखा है तो वहाँ पे n चाहिए होगा ना?
Over here.
Yes, I think.
Good guess, but we are essentially trying to add the factors to this one, right? So if we were to take n over here, we would basically be multiplying it as many times as it has factors. So if it was 1 over here, 1 divides n completely, then we'd be adding n to the sum, not 1 to the sum. So that's why this is supposed to be I. That part is correct, but good guess. The others?
I less than or equal to n by 2.
That is correct. So this is supposed to be less than equal to, since we also want to check n by 2. So now if we run this one and we input 28, it is working well. If we run this again and let's say I enter 18, 18 is not a perfect number, so it works. Once again, let's say I enter 6,
It's perfect.
it is perfect. So the code works perfectly fine now. Once again. So that was this first question. Shall we move on to the next question? So let's take this one. So the question is, write a C program to print all Armstrong numbers between 1 to n. I guess I should clarify that I mean 1 to n over here. So yeah, an Armstrong number equals to the sum of the cubes of its digits. Okay, so we want to print all the Armstrong numbers between 1 to n. So first, let's just see the code for printing a single Armstrong number. So what do we have to do first? Firstly, I'll just put a
To,
sum over here.
we need to pick the every digit from that number
Right. So how will we take the digits?
with modulus.
Can you please explain?
Uh, we'll first simply n modulus. The last digit can be pick out by n modulus 10. While n modulus, we can get the last digit value.
That is correct. So we can do n modulus 10 in order to get the last digit,
Yes, yes,
right? So in order to get each digit every single time, we'll need a while loop. And in this while loop, we can just directly put in n. Yeah. And after that, uh, yeah. So we have n over here. Now we can just check, or we don't even have to check. We can just do sum plus equals. Already Visual Studio has given the answer, but yeah, we can just multiply the last digit 3 times in order to get the answer. uh, do you understand why we are doing that?
yeah, I have seen already, but it is can you please explain once
Right.
how it is
So
working this simple line?
yeah, so this is essentially we are taking the last digit and we are cubing it or multiplying it 3 times. And after that, what do we have to do in order to get the next digit?
Simply n should becomes the quotient value.
That is correct. So we simply divide it by 10. Is that okay?
Yeah, fine.
So essentially, what this code does is that it will take the last digit and it will cube it and add it to the sum, and then it will divide the number by 10. So it will bring the next digit forward. Okay, so that way it will calculate all the what is it called? It will calculate this part, the cube of the sum of cubes of the digits. So now what we have to check is uh, if the sum equals n, we'll just print the sum, right?
Yeah,
So that is essentially we are checking if the number that is given is an Armstrong number,
yes, yes.
right?
But our n becomes 0 after while condition.
Right. So now we have finished one part of it. We have figured out how to find the Armstrong number, whether something is an Armstrong number or not. And if it is, we are printing it. Otherwise, it is not doing anything. So now, how can we convert this or not convert. How do we modify this code in order to print every single Armstrong number between 1 and a given n?
Again, writing some range, checking every number for this part.
That is correct. So for int I equals 0 to I less than n, so I plus plus, we can just take all of this and now it is in a for loop. Now one thing that we have to do is we have to change these n's all to i's. Can you tell me why?
Because we are checking numbers as I, not a fixed value.
That is correct. So we are checking the instances or the iterations one by one. So first we are checking 1, then 2, then 3, then 4, up until some number n. So now this is the code, and I say that the code is ready. So should we test this?
Yeah.
Okay. So now then, let's say that I want between 0 and 100. So it is telling that there are 0 numbers between 0 and 100. And from the sample input, we can see that that is true. If we run this again, 1 second. I think I may have added something. Okay, 1 second. Uh, okay.
After completion of while loop, whenever we are checking that condition is not satisfied with I, and I becomes 0
Sorry.
after while condition in for loop.
Right. We are checking with 0 also, right? So that's why I guess the error is coming. Yeah.
So we'll simply put that I into some any n value or any other variable like temp.
I don't really know why it's acting like this, no?
I think we need to add increment in while loop because it's
It's fine.
not checking all.
It's fine. It's fine. Like the reason why it did not work is because we had a 0 over here, right? So I guess that was causing some issues. Like this while loop was not running at all, and then it was causing some other stuff. But yeah, now it should be fixed. Let's see. Okay, what's going on over here?
I think we should add increment plus plus and kind of thing.
I mean, it is incrementing this one. I'm just
So,
not sure
one,
where it is going wrong.
one thing I want to clarify: whenever we are entering into for loop for the first time,
Okay.
after that becomes something like I slash equal to 10. Then after while becomes false, only I becomes 0. When I becomes 0, while becomes false, then it will come out of the while loop. Whenever it is checking sum equal to I, so
So we need increment in while loop, I think.
I mean, in the case of while loop, we are decrementing it, like we are dividing it by 10 every step. So it is checking like the digits each time. So if it is like one digit, it will run once. If it is two digits, it will run twice and stuff like that. But yeah, I'm not really sure where we are getting the issue.
So let me tell you one thing. Can I?
Yeah, go ahead.
After entering into for loop, let me put temp equal to I.
Okay.
Let us then I is going to enter into temp. Then in while we'll use temp value, while of temp, then temp modulus 10, temp modulus 10, temp
Oh,
modulus
right,
10.
right. Yeah, I get you. Yeah.
That is what
So you're telling like this, right? Since
yes,
it is
that's
always going to be sum is never going
zero.
to be zero. Yeah.
Yes.
Yeah, good catch, good catch. Yeah, so now if we run this, it should work. So uh,
I think we need to change I in temp also, or not. No, no need, no need. Correct, correct. You are correct.
uh, why is this going into debugging mode? Um, okay, leave it. What you can do is just I'll paste the question in the chat. I'll just paste the question in the chat, and after that you can just try it out on your own. Raised to the power of digits in that same number. Okay, is that so? Um, yeah, that does complicate it.
So shall we
This
print
will.
that number?
Sorry.
Shall we print which number that is calculating? Then 153 is usually, we know it is Armstrong.
Yeah, 1 second. Let's just see. I don't know why it keeps going into debug mode. It is not incrementing in the slightest. I see. Hmm. Yeah, for some reason it's not incrementing the number. So I guess it's some issue over here in the for loop. Either that or this one, I guess.
I think we should increment n also.
Honestly speaking, I'm not sure. Like this code should work. Let's try. Let's try it on Replit.
Any online compiler or GDB compiler.
Yeah, yeah. So okay, over here also it's doing the same thing. Now why is that doing this same thing? Just one second. So in cases like that, usually it's the for loop that's it's usually the while loop that's causing the issue. So why is it causing it like that? So okay, we have initialized n and sum over here. We are using I over here, I less than n. Okay, temp we are initializing it as I. Uh, while I is greater than 0, sum plus equals this one. I is that one. So we are dividing it by 10. Just one second.
Everything is fine, sir. Somewhere.
Yeah. So n by 10, if we print it, what will it give us? Yeah, it gives us 0. So that
Yes.
part is fine. Uh, let's just try this one. Yeah, this also works just fine. Why is this not stopping?
Sir, in while loop, if you use printf, it will be looping number of times, no, sir.
So
Sir, in while loop, if you use printf, it will be printing the number of loops, sir. It will be going for infinite, no, sir.
If we were to just try this over here. So it just keeps going like that. Okay, so it just keeps on incrementing for some reason. So why is this not working?
Printing the sum before checking the condition sum is equals to temp or not, sir. In while loop, if you use the printf, it will be printing the sum above and it will be incrementing the next number.
I mean, see, this one does not really affect I. This is simply just updating sum. And then we are printing sum, it is not updating anything. The main issue is this I is not getting divided or something.
So it's printing the sum above sum only, sir. You have printing the sum just below the sum condition. You have not checked. You have not checked it, sir.
No, I'm just debugging this one. This is for debugging. The main is this one.
Okay.
Because I inserted 10, but it is going up to like 370,000 or something like that. So that's the thing. Okay, leave this one. I'll just paste this code here. If it even wants to go fully. Otherwise, I'll just paste a problem sum.
Overall. Oh, yes, thank you.
Yeah.
Overall code also. Yes, we'll see in our process.
Yeah, just check it out. Although don't worry too much about it. Like this was just to, practice some loops, some, conditional statement concepts. So it is not really that important. So I hope that you guys at least understood like some of this theory part. And so, yeah, do you guys have any other doubts that you'd like to get clarified?
I wanted to ask why do we add hashtag in the header file, like hashtag include str login.
Okay, you're asking about this one, this one.
Header file.
Okay, see, so this is something that is like at this point in time, like up until week, I believe 11 of yours, like week 10, week 11, you do not really have to worry about this one. Just think of it like hashtag include is a keyword, and stdio is simply the library that you want to use. So let's say that I want to use some math. Already it is showing, right? So this simply tells me what functions I can use. So for example, I imported math.h. I can use stuff like absolute function or floor function or power function. So that is what this means. Other than that, this hashtag include, just think of it as a keyword. You don't really need to worry too much about what this stuff means. Just know that this hashtag is something like this int or this curly brace. It's just a part of the syntax.
Okay.
Okay. If you guys have any other doubts, feel free to say it now. Otherwise, we can end the session. All right, then I'll take that as you guys don't have any other doubts. So,
can we
yeah, Kamali.
connect any LinkedIn or something?
Sure. Like I have my TA classes every Wednesday, Friday, and Sunday. So you can find me on that. Otherwise, I'll just put my email on here. You can Gchat at any time.
Sure, sir, sure. So which classes you usually take, sir?
Mainly only for C programming.
Okay, okay.
So yeah, all the best for quiz 1. Make sure you guys get some sleep, because even if you prepare well, if you are feeling sleepy in the exam hall, it is not going to be a fun experience. So yeah, I'll just be ending the recording now.